All right, what would you guys like to talk about today?
Can we do a problem on the newest web work, the homework 8?
Sure, which problem are you interested in? I think that was Aiden.
Yeah, it was. Can we do problem 1 and then I wasn't understanding how to find the power across the 2.5 volt um voltage source and then power across the I think that would be the converted source as well.
Okay, so let's just go through the whole thing here.
Okay.
So, um, since you asked the question, let me log in under you, and then we'll use your numbers, and everybody else can just kind of figure stuff out. All right. Like your last name. Sorry, there we go. Sorry, I'm old. That was Austin Gatlin, or if I'm mixing things up.
Oh yeah, it is.
Okay. Austin Gatlin, homework 8. Actually, I'm looking at the wrong damn thing. Sorry. Homework 8, problem 1. All right. So, um, the circuit that we're looking at looks something like this. And I'm going to use um, changing the direction on a current source to get rid of that negative sign because I just don't particularly like having negative currents or voltages for that matter. So that's why I'm drawing this one down with a value of positive 5.5 amps. Then we have a resistance here. Um, I'm going to leave this as RL because we're going to play around with that. I'm also going to make a note on the right-hand side here that at least for part A, RL is equal to 11 ohms. Let's see, we have the negative polarity terminal on top, positive polarity terminal on bottom. This is our voltage Vx. Then over here, we have a 10 ohm resistor and then a voltage source. And once again, your numbers are negative, so I'm going to put the positive polarity terminal on bottom just to get rid of that pesky negative sign. So I believe I have drawn the circuit correctly here. In part A, we are asked if RL is equal to 11 ohms. We want to find Vx and the power supplied by the 9 volt source. Okay. So for this particular part, we can really do anything that we want to do. So I think quite possibly the easiest way to go about solving for the quantity Vx might be nodal analysis or something like that. Okay. So if we were doing nodal analysis to this particular circuit, I might choose my reference node to be here. And I would have a nodal voltage VA at the bottom node, a nodal voltage VB at the top left-hand node, like so. And those are my only two nodes that aren't my reference. So we can say right from the jump that VA is equal to 9 volts. KCL at node B tells us that 5.5 amps plus VB minus VA over RL, which in this case is 11 ohms, plus VB over 10 ohms is equal to 0. And if we substitute in 9 volts right here, this is a one equation, one unknown system. So I'm going to throw that in my numerical solver on my calculator real quick and solve for VB. So let's see, so that's going to look like x over 11 plus x over 10 will be equal to 9 over 11 minus 5.5 amps. So all of my VB terms are on the left-hand side, all of my constant terms are on the right-hand side, and I'm solving for what my calculator is calling x. And I get, after it thinks about it for a moment, VB is equal to negative 24.5238 volts. And from this, my voltage Vx is simply VA minus VB. So that's going to be 9 minus that quantity, which came out to be 33.5238 volts, which looks like the number that you have there. So that seems pretty legit. For the power supplied by the 9-volt source, we need to know the current that is flowing into the negative polarity terminal. I'm just going to call this I 9 volts. Let's see what's going on in chat here really quick. Can we do question 6 on homework number 8? Caleb, absolutely. Just let me get finished with this one first. Let's see here. So what's the easiest way to solve for this current? So I think the easiest way to solve for that current would be taking this current and this current together. So I 9 volts is going to be Vx over RL minus 5.5 amps. So I have that in my calculator already, so that's just going to be the answer that I had divided by 11 ohms minus 5.5 gives me a current of negative 2.4523 amps. Multiply that by 9 volts. And we get, at least I got, negative 22.071 for watts. Let me just check some things really quickly. Yep, so that is indeed the correct answer. Austin, do you have any questions about what I did here, particularly solving for the current and then the power? Not to put you on Front Street, but that's the part that you got incorrect.
No, thank you.
Okay, so let's look at part B now then. So in part B, we are going to keep the load resistance RL the exact same, and we are going to transform the practical voltage source into a practical current source, find Vx, and then the power supplied by the new ideal current source. So I'm going to redraw my circuit to some extent. So this is still going to be a 5.5 amp source direction down. My resistance RL is still just going to be an 11 ohm resistor. Now I'm performing a source transformation. So my 10 ohms in series with my 9-volt source is going to look like 10 ohms in parallel with a current source direction down. And the value of that current source should be 9 volts divided by 10 ohms, or 0.9 amps. Hopefully if that mental math there is correct. The voltage Vx is then just the voltage drop across those two resistors in parallel. So realistically, we shouldn't have to do any extra math whatsoever to solve for the voltage Vx, because if we replace the right-hand side of the circuit by an electrically equivalent thing, it's going to be the exact same thing. But just to check and make sure we've done things correctly, we could solve for it very easily. So both of these currents are flowing down, so I can add them together. And so I can say pretty easily, just using Ohm's law, that Vx is going to be 5.5 amps plus 0.9 amps. My two current sources are in parallel, so I'm adding them together. Both of those currents are going to be flowing into the positive polarity terminal. So over here, I'm just going to have 11 ohms times 10 ohms over 11 ohms plus 10 ohms. And we should get the exact same value for Vx. So let's just check things out here. 5.5 plus 0.9 multiplied by 11 times 10 over 21. And we got 33.5238 volts, which is exactly what we got earlier. Sorry to interrupt. Jake just asked a question regarding the exam. When you are finished with the exam, or excuse me, he asks, when we are finished with the exam, do we need to stay online in the test to scan our work and submit it to your email, or can we do it immediately after the test? So Jake, you do not need to stay online in the test to do it at all. I do not have, there is a thing on responses to make you guys do that. I didn't want to do it because it just sounds like a headache. So what I've done instead is I have opened up an online submission portal, much like for the in-class assignments. And so after you complete your test, you will simply scan your work and then submit it to that online submission portal. The online submission portal will close at midnight. So you have plenty of time after you take your exam in order to scan your work and get it submitted. So you don't need to feel rushed or anything like that. All of the time that is dedicated for you to take your test, the full 3 hours, is for you to actually take the test. So I'm not going to take any of that time away by making you scan your work within that window. Is that clear? No problem. All right, let me get back to this homework problem here. All right, so we're still now trying to find the power supplied by the new ideal current source, which is this current source over here. Well, luckily for us, since everything is in parallel, the voltage drop Vx is just the voltage that we just found is the voltage drop across that new 0.9 amp ideal current source. And awfully convenient for us, the current is flowing into the negative polarity terminal. So the power supplied by the 0.9 amp source is simply going to be Vx times 0.9 amps. So 33.5238 volts times 0.9 amps comes out to be 30.1714 watts, which also happens to be the correct answer. Any questions or comments about part B? Austin?
I'm just a little confused on why they call it an ideal source. I thought that would be a practical source.
So the 0.9 amp source by itself is an ideal source. The 0.9 amp source in parallel with the 10 ohm resistor is what forms the practical current source.
Okay, thank you.
So now that we have this thing right here, we're looking for part C. What value of RL will absorb the maximum power, and what is the value of that power? So let's use our circuit from part B. So we've got a 5.5 amp source direction down. Now we have RL. We have our 10 ohm resistor over here. And here we have a 0.9 amp source. We're not looking for this voltage Vx anymore in particular, but I'm just going to put it there. And we want to make this look like either a practical voltage source in series with the resistance RL or a practical current source in parallel with the resistance RL. So I think very easily that we can get this to look like a practical current source in parallel with RL simply by adding those two ideal current sources together. So our circuit would look something like this. So here's our resistance RL. Here is our 10 ohm resistor. And then this is going to be a current source that is 5.5 plus 0.9, I believe is 6.4. You guys might want to check me on that. I am terrible at simple math. But if that is correct, then our load resistance needs to be 10 ohms in order for maximum power to be transferred. And then our maximum power is just going to be 1/4 times 6.4 amps quantity squared times 10 ohms, which, let's see, 0.25 times 6.4 squared times 10 gives me a power of 102.4 watts, which is correct. So that was homework 8, problem 1. Austin, any last questions before I move on to answer Caleb's question?
No, I would like to look at 4, but you can move on to the other question before we do that.
Okay. So you
Dr.
want to
Hardman, I had a quick question. Why
okay.
is RL like I'm just trying to understand why RL is equal to 10.
So let me put some terminals here really quickly, right? So
Mhm.
everything to the right-hand side of this this set of terminals is a practical current source. From our lecture on Monday, in order for maximum power transfer to occur, our load resistance RL has to equal the source resistance of our practical source. So this RL right here has to be the same as this resistance in order for maximum power transfer to occur. And we derive that on Monday. So if we have a 10 ohm resistor here, we just plug that value in for RL, and that's going to let us know what maximum power transfer occurs.
Okay, yes, sir. Thank you so much.
No problem. All right. So let's see. Caleb, you were asking about question 6 on homework number 8. So let's see, student progress, Latrell, 8. problem 6. Okay. So let me draw out the circuit that we're looking at. So homework number 8.6. So I have a current I1. Caleb, I'm using your numbers. So you had a positive value for this, so I'm going to leave it direction up. And it's 9.5 amps. Then we have a resistance R1, where R1 is 12 ohms. We have a load resistance RL up here. We have a resistance R2 that has a value of 10 ohms. R3 is 12.5 ohms. R4 is 20 ohms. Penmanship got crappier than normal. My apologies. And then we have a voltage of V1, negative polarity on top, but your particular value for V1 is negative, so I'm going to get rid of that negative sign by flipping the polarity. So this is going to look like positive 5 volts, positive polarity on top. And we are asked to find the maximum power that RL can absorb. So effectively, we are just going to do a few source transformations until we get this to look like either a practical voltage source in series with the load resistance RL or a practical current source in parallel with the load resistance RL. And I can tell personally just by looking at this that we're going to wind up having a practical voltage source. So what I'm going to do is I'm going to perform a source transformation on the practical current source on the left-hand side of the circuit, and I'm also going to perform a source transformation on the practical voltage source on the right-hand side of the circuit. So for my practical voltage source, or my practical current source transformation over here, excuse me, what I'm going to do is I'm going to have a voltage source here that is 12 ohms times 9.5 amps. So that's going to look like 114 volts. And I'm putting it in series with a 12 ohm resistor down here. And just to be really clear, these are the terminals that I disconnected and I'm reconnecting things to. And let me do a set of green terminals over here. So here's my load resistance RL, my 10 ohm resistor, my 12.5 ohm resistor, here's my set of green terminals where I'm going to reconnect the transformed practical current source. So let's see, so 5 volts in series with 20 ohms is going to look like a fourth of an amp in parallel with 20 ohms. My current source should have a direction up because the positive polarity terminal on my voltage source is on top. So 5 divided by 20 is 0.25 amps. So now I see that that 12.5 ohm resistor and that 20 ohm resistor are in parallel, so I can combine them. So 12.5 times 20 over 32.5 looks like 7.692. Ohms and some change. And now I am going to source transform my practical current source back into a practical voltage source. So my next redraw should look something like this. Here's my red terminals. Here's RL. Here's a 10 ohm resistor. Here's my green terminals. Let's see, times 0.25. So we are going to have a 7.692 ohm resistor in series with a 1.9231 volt source. And so what I can do now is I can add those resistors together and add those voltage sources together because everything is connected in series. And so what this is going to look like, so I'm going to have 114 volts minus that 1.9231 volt source because they are in series but are opposite polarities. So 114 minus answer gives me 112.0769 volts. I'm going to combine the 12 ohm resistor, the 10 ohm resistor, and the 7.692 ohm resistor into just a single equivalent resistance. So 12 plus 10 plus, let me scroll up here so I don't have any rounding error. So this is going to look like 29.6923 ohms. And then here is my resistance, RL. So if we want to know the maximum amount of power that RL could absorb, that is going to be 1/4 times that 112.0769 volts quantity squared divided by that 29.6923 ohms of resistance. Let me throw that in my calculator real quick. So 0.25 times what I have stored in my calculator as x squared divided by what I have stored in my calculator as y gave me 105.7617 watts. And let's just check. That is indeed the correct answer. So Caleb, did you have any questions about that particular process? All right. Riley, how may I help you?
So why was the 114 positive rather than negative? The combined.
Why was the so I may be misunderstanding your question. I thought I heard why was the 114 positive?
Yes, sir. Whenever you combined the voltages, it was positive 114 minus the 1.9231. So why was the 114 the positive one? I think I'm missing like a small step there.
Oh, okay. So effectively, I made an assumption here that my current flowing around this circuit was flowing this way. So effectively, I was trying to figure out what the voltage source on the left is going to look like. So if I follow this current around, we hit the negative polarity terminal of the 114 first. We hit the positive polarity terminal of the 1.9231 first. So because we hit the different terminals, that's how I knew to subtract. Because the 114 has positive polarity on top, the 112 should have positive polarity on top. If instead I had chosen to put my voltage source on the right-hand side of the circuit when I redrew things, I would have wound up doing 1.9231 minus the 114, and that would have given me the negative value. So effectively, I'm using this one as my reference, which is why I got a positive number. If I had chosen to do this one as my reference, I would have wound up getting a negative number.
Okay, that makes sense.
All right. Any other questions about this one before I answer Austin's question about number 4 from this homework set, if I'm remembering correctly? All right, so let's go back to student progress. Austin, homework 8, problem 4. Okay, I actually really like this problem, and I understand very explicitly that you guys hate it, but it'll be okay. One of the things that's really gross about it is that for whatever reason, you're given numbers that are out to like 10 decimal points or something asinine like that, but we'll make it work. Okay, so let's see. So homework number 8.4. So we are told that a certain practical current source, so I'm going to draw a practical current source here really quickly. So here's IS in parallel with some resistance RS. Provides some amount of power, I'm about to write that out, to a 120 ohm load. So I'm going to go ahead and draw a load resistance over here on the right as well. And we are told that the power absorbed by our load is 0.194675925 925 926 watts when RL is equal to 120 ohms. And we are also told that the power absorbed by our load is 0.345 244 126 124 552 watts when our load resistance is equal to 470 ohms. And then we're asked a series of questions. So the hardest part of this particular problem is figuring out what the value of IS and RS is for this particular practical current source. Once we have those two pieces of information, then actually determining what the question asks is fairly straightforward. So let's figure out the hard part first, okay? So effectively, let's call this PL1 and RL1, and this PL2 and RL2. So we know that the power absorbed by our load resistance is going to be the product of our load voltage times our load current. So I'm just going to write here VL times IL. We can find VL by using Ohm's law. So that's going to be IS times RS times RL over RS plus RL, where RS times RL over RS plus RL is nothing more than those two resistors in parallel. And then our current IL could be found by using current division. So that would be IS times 1 over RL divided by 1 over RS plus 1 over RL. And this is a kind of identity thing that we used the other day. This bit right here is the exact same as IS times RS over RS plus RL. And from that, we can say that our power is IS squared times RS squared times RL over RS plus RL quantity squared. So effectively, since we have two values for PL and two values for RL, we have a two equation, two unknown system. Now there's some polynomial stuff going on in here that makes it a little gross. So personally, I would solve this system using MathCAD because it can handle it. I don't know that the calculators can handle solving a system when you've got polynomials buried inside of there. Okay, so that's the hard part of the problem, is effectively recognizing that since I have one power and an associated load resistance and a second power and a second load resistance, I can use this relationship that PL is equal to IS squared RS squared RL over RS plus RL quantity squared in order to determine what IS and RS are. Do you want me to set that up in MathCAD, or are you good, Austin?
No, that's okay. I realized I set it up wrong the first time.
Okay. So once we figure out what IS and RS are, then effectively we're asked a series of questions. Okay. So for part A, we want to know what RL is, what VL is, and what IL is when VL times IL is at its maximum. Okay. So when VL times IL is at its maximum, so what is VL times IL?
It's power.
Exactly right. So part A is just saying, hey, what's happening at maximum power transfer, right? So we can see very easily that RL is just going to be the RS that we solved for. VL is just going to be IS times RS squared, because RL and RS are the same thing, divided by twice RS. So that's nothing more than IS RS over 2. And IL, so just using current division where both of our resistors are the same, is just going to be half IS. So the current's going to divide evenly between those two identical resistors. For part B, we want to find RL, VL, and IL when VL by itself is at its maximum. Okay. So I'm going to draw our circuit here really quickly, and we're going to talk our way through this. Okay. So here's IS. Here's RS. Here is the voltage VL. And then here is our resistance RL. So our ultimate goal here is to make sure that our voltage VL is at its maximum possible value. We can observe, I think, pretty easily that if RL has a value, then that's going to make the voltage VL smaller, right? Because the voltage VL will just be the voltage drop across RS in parallel with RL. So effectively, what we want to do is figure out how to make RS in parallel with something as large as it could possibly be. And that occurs when RL is an open circuit. So when we want our voltage to be at its maximum, effectively we are trying to determine the open circuit voltage of the system. So that means that RL will be infinite, which I believe you can just put into MathCAD as, there's going to be not MathCAD, WebWork as INF. VL will just be IS times RS, and IL must be 0 because our load resistance is an open circuit. Seven, number 1, part D. Absolutely, Ian. After I knock this one out. So for part C, we have a similar thing. Our goal is to figure out RL, VL, and IL when our current, IL is at its maximum. So let me draw our current IL here, right? So what value of RL do you think is going to cause the maximum amount of current to flow through our load? Anybody have any thoughts here?
Is it 0?
Exactly right. So when our load resistance is a short circuit, that means that all of our source current will flow through the short, bypassing that resistance RL. If the value of RL is anything larger than 0, then that means that some of the current will flow through the resistance RS, therefore making IL smaller. So great intuition there. So RL has to be 0. VL will be 0 because the voltage drop across the short circuit is always 0. And IL will simply be IS. So Caleb, let me answer Ian's question first, and then I will look at yours. So before I move on to Ian's question, does anybody have a question about this particular problem? All right. So Ian asks about homework 7, number 1, part D. So let's go to student progress. Swanson. Homework 7, number 1. So homework number 7.1. In part D, so let's see here. Let me draw the circuit out. We are going to have, this is using Ian's numbers, so V1 is 4.5 volts. Then I have a 10 ohm resistance up here. 40 ohm resistance here. A 20 ohm resistance here. We have this generic circuit element A, and we're told that for this particular part, we have a 14 ohm resistor in series with a dependent current source. So here is my 14 ohm resistance. Here is my dependent current source. The arrow is pointing to the left, but we're also told that it is negative 1.2 Vx. So I'm going to do this as positive 1.2 Vx, arrow pointing to the right, because I just really don't like having negative sources. We're going to have a 30 ohm resistor down here. And we have a voltage V2 like so. And V2 has a value of positive 1.5 volts. So this is the circuit that we're trying to analyze, and our ultimate goal here is to solve for the voltage Vx. So because this is from homework set number 7, we are expected to do mesh analysis for this particular problem, but I want to look at things here and just make sure that that's the best way to do things. So I can see very easily that there are only 3 meshes in this circuit. As far as nodes go, there's one at the top left, one at the top right, one in the middle, one between the 14 and the 1.2 Vx dependent source, one on the right middle, and then one at the bottom. So I believe that's like 6 or 7 nodes. So mesh is definitely going to be the easier thing to do here. So we will do mesh. So I'm going to define my mesh currents. So this is going to be a mesh current IA. This is a mesh current IB. And this is a mesh current IC. I have a controlling variable since I have a dependent source. So our equation for that is going to be Vx is equal to 20 ohms times IC minus IA. And by the way, if anybody has any questions about any of this, please stop me and I'll be happy to explain things. We have a current source. So I'm going to have a current relationship equation. So that's going to look like 1.2 Vx is equal to IC minus IB. Now I'm going to write my KVL equation around my supermesh BC. So that's going to look like 20 ohms times IC minus IA plus 40 ohms times IB minus IA minus 1.5 volts plus 30 ohms times IC is equal to 0. And then I'm going to write my KVL equation around mesh A. So that's going to look like negative 4.5 volts plus 10 ohms IA plus 40 ohms, IA minus IB plus 20 ohms, IA minus IC is equal to 0. I have 4 equations and 4 unknowns, so solving this system should allow me to calculate Vx.
Thank you. I just wanted to make sure that 14 ohms in series with the 1.2 Vx, is that just kind of irrelevant?
So it's very similar to the in-class assignment problem, right? So because that middle branch there that's shared between mesh B and mesh C contains a current source, we are going to avoid it with our KVL equations. And as a consequence of that, the 14 ohm resistor isn't actually going to show up. Once again, because we know we can solve for what 1.2 Vx is, the voltage drop across the 14 ohm resistor is effectively a known quantity. It's just 14 times 1.2 Vx. So that's why we don't need it. It's not providing any new information whatsoever.
Okay, thank you. Just wanted that theory behind that.
Yep. All right, Caleb, let me see. You were asking about, hold on. Question 16 on fall 2019. So let me look at that. And then specifically, where the voltage Vy is a short circuit. So the voltage Vy being a short circuit, I think personally makes a couple of these things significantly easier. So let's see. So this is fall 2019. Number 16. And it's going to be modified just for sake of argument here. So tell me if I'm drawing the circuit as you expect, please, Caleb. So I've got a 6-volt source here. I have a resistance R1 that is 9 ohms, cross which I have a voltage Vx. I have a dependent source that is twice Vy. You specifically asked for Vy to be replaced by a short circuit. So this is my voltage Vy, and it's definitely just going to be 0. Here's a resistance R2 that is 7 ohms. And then lastly, I have a voltage source over here that is 3 Vx. So because I have that short circuit in the middle, sorry, let me stop here. So Caleb, this is what you're asking me to solve, right? Or did I misinterpret your question? Okay, so since the voltage Vy is definitely 0 because it is the voltage drop across a short circuit, then our dependent source 2Vy is providing exactly 0 volts. So we can replace this 2Vy voltage source with a short circuit without losing any information whatsoever. And then now this Vy doesn't really mean anything. I'm just going to leave it there for the sake of argument. So we're trying to solve for the voltage Vx. Well, Kirchhoff's voltage law around this loop tells me that Vx is 6 volts because the 9 ohm resistor is now in parallel with the 6 volt source. So I'm done. What's next?
Can you work out that problem the regular way?
Sure. Y positive polarity on bottom, negative polarity on top. Okay. So this is what's commonly referred to as a single loop circuit, meaning that all of the elements are connected in series. So there is going to be a common current that I'm just going to call I that's flowing through all of these elements. Okay. So if I were to write a KVL equation around the outside of this circuit, I would get the relationship negative 6 volts plus 9 ohms times I plus twice Vy plus 7 ohms times I plus 3Vx is equal to 0. So I currently have one equation and 3 unknown quantities. So a very easy equation that I can come up with is just from Ohm's law, and I can say that Vx is simply 9 ohms times I. And now I'm going to need a third equation. And so my third equation is going to come from either of these two equations. So I could do KVL, sorry, I meant to do a different color there, around this loop or path, or KVL around this one. I'm going to choose to do KVL around the left-hand one, but either one would work. So that's going to look like negative 6 volts plus 9 ohms times I plus twice Vy minus Vy is equal to 0. And now I have 3 equations and 3 unknowns, so I can solve for everything I want.
Thank you.
No problem. What do we want to look at next?
So I actually have a simple question about number 15 on that same exam.
Sure.
So when you're doing the path of the resistances and stuff, I was checking your solution and you like cut out the path of R 20 ohm and 14 ohm.
Mm-hmm.
And I was just wondering why you did that.
Because it's in parallel with a short circuit, and anything in parallel with a short circuit doesn't count. So let me explain that really quickly, because I don't know that we've talked about it before. I just kind of assumed that you guys knew it, which may have been incorrect. So let's just say that I have 2 resistances in parallel. Okay, so here's a resistor R1, and here's a resistance R2. We know that the equivalent resistance can be expressed as R1 times R2 over R1 plus R2.
Hmm.
If either of those resistors is 0, which would be a short circuit, then the equivalent resistance is 0, because I have a something times 0 in my numerator. So I threw all of that away because I can combine that R in series with 20 in series with 14 to get, let's see, I think that would be 45. But 45 in parallel with a short circuit is still a short circuit.
Okay, yes, sir.
All right, what else are we going to talk about?
Can you work out numbers 24 and 25 on winter of 2019?
24 and 25. Okay. So winter 2019, number 24 and 25. So let me draw things here really quickly. We've got a 4 ohm resistor up here. Short here. 2 amp current source. Short across here. Here I have a resistor in series with a voltage source. So this is 7 ohms and this is 8 volts. I've got a 3 ohm resistance here. .5 IY. That 5 doesn't look particularly 5-like, so let me fix that. Six ohm resistor over here. Our current IY is the current that's flowing through the 4 ohm resistor, and our voltage Vx is this voltage. All right, so the first thing I'm going to do is I'm going to rewrite Vx to make it look less asinine, okay? So the negative polarity terminal is associated with this node. The positive polarity terminal is associated with the bottom node. So I could just as easily say that Vx is nothing more than the voltage drop across my 3 ohm resistor, positive polarity on bottom. So that makes things a little less confusing now. So now I need to figure out which analysis technique to employ. So I think I'm going to wind up doing nodal analysis. So let me explain my reasoning here. I definitely have 4 meshes. If I identify my nodes, I have this one node right here on the top left. I have this node on the top right. I have this node on bottom. I also have this node right here, which I notice a lot of students miss when it's just 2 things in series. There is a node between them, so I want to be clear about that. Because I have a voltage source, I like to make sure that my voltage source is touching my ground node. So I'm just going to choose the bottom node as my reference. So I'm going to call this VA, this VB, and this node right here VC. Okay, so I've got 2 different controlling variables. So let's start with Vx. Vx is going to be 0 minus VA, so that's just negative VA. Iy is going to be VA minus VB over 4 ohms. I have 1 voltage source, so I'm going to have a voltage relationship equation that just says that 8 volts is equal to VC, and now I need to write a KVL equation at node A and a KVL equation at node B. So KVL at A is going to look like VA minus VB over 4 ohms. Plus 2 amps plus VA over 3 ohms plus VA minus VC over 7 ohms. So just so we're clear here, I have this current leaving node A, this current leaving node A, this current leaving node A, and this current leaving node A. So 1, 2, 3, 4 different currents and 1, 2, 3, 4 terms. So that seems like we're good to go. For node B, I'm going to do something similar. So I'm going to have VB minus VA over 4 ohms. Negative 2 amps plus 1.5 IY. And lastly, VB over 6 ohms. Set this equal to 0, solve our system, and we should be able to get Vx and Iy from this information.
Thank you so much.
No problem. So on a completely and utterly unrelated note, is anyone else having issues with allergies, or do I just need to trim my mustache? Because my nose is itching so much right now. So one person says I need to trim my mustache, and another person says that allergy season is on us. I think it's allergy season as well. My mustache isn't as long as it has been previously, although anyway. My dog is having issues with allergies, so that's always fun. He's just walking around sneezing everywhere. So anyway, what else are we going to look at today? Oh, let's see. Caleb asked, sorry I missed this earlier. Could you show us a question involving a derivative? So do you want me to just make something up that is going to entail using a derivative? Or do you have a specific question in mind? Okay, so just make something up. All right. So where we're at right now in our circuit analysis, there's really only 2 places where we could be expected to have to use a derivative. So option 1 would be if we had some charge as a function of time, we know that our current is related to the derivative of the charge. And our second option would be if we had an energy as a function of time, we know that power is simply the derivative of energy with respect to time. When we learn about inductors and capacitors and all of that kind of stuff, we'll have some other derivative-based relationships. But for right now, these are the only 2 places that I can think of off the top of my head where we might have to use a derivative. So let's say, just for the sake of argument, that we have a charge of 5t plus 8e to the negative t coulombs flowing through some particular element. So our current would then be 5 minus 8e to the negative t amps. Because 5 minus 8e to the negative t is the derivative of q of t. So on your exams, and for the most part throughout the entirety of this course, I'm really only expecting you to be able to take the derivative and the integral of simple polynomial functions, so like, t squared, t cubed, that kind of stuff, exponential functions, and sine functions and cosine functions. There really won't be anything else that we'll have to deal with. So if you can do the integral and derivative of those things, or since we use numbers and stuff like that on tests for the most part, if you know how to use the integral and derivative function of your calculator to evaluate a particular thing at a time, you're good to go. I had us use the quotient rule in a derivation on Monday, but I wouldn't expect you guys to be able to just crank that out off the top of your head on a test or anything like that. Just to add on a little bit, so sometimes you might be given a graph and you will have to apply either an integral to that graph or a derivative to that graph. So for a graph and the integrals, it's pretty easy. You're just going to be adding up areas. So I'll always try to make sure that it's just simple shapes like right triangles, squares, and rectangles. For derivative-based things, you're just looking at slopes effectively. So shouldn't be particularly difficult there. RL question on the 2020 exam. So fall 2020. And I think you're referring to either question 25 or hold on. Question 20 and or 21. So we have the following circuit. An 11-volt source in series with an 18 ohm resistor. 2 amp source. An 11 ohm resistor. 14 ohm resistor. A 7-volt source. And then here is our resistance RL. So our ultimate goal here, as per usual, is to simply have a circuit that is a practical voltage source in series with the resistance RL, or a practical current source in parallel with the resistance RL. Looking at this one, I'm not sure which we're going to end up with. So I would start for sure by doing a source transformation on the practical voltage source on the left-hand side of the circuit. And the reason why I'm pretty sure I'm going to do that, in order to do 21, we're going to have to do 20 anyway. So we'll knock them both out. So performing this particular source transformation is going to allow me to combine some current sources. So let me show you what I mean by that specifically. So we're going to have a current source that is going to look like 11 over 18 amps. in parallel with 18 ohms. Here's my red set of terminals. Now I'm going to have a 2 amp source. That is a resistor. My apologies. $11 ohms, 14, 7 volts. And over here is RL. All right, so my 2 amp source and my 11/18 amp source are now in parallel, so I can combine them. So 2 amps is the same as 36/18. 36 plus 11 is going to make this look like 47 if my mental math is correct. Please tell me if it is not. And now what I'm going to wind up doing is source transforming the practical current source on the left back into a practical voltage source, which is going to allow me to combine the 18 ohm resistor and the 11 ohm resistor, right? So 47 amps, 47/18 times 18 is going to look like 47 volts. Here's my 18 ohm resistor, my red terminals. Here's my 11 ohm resistor, 14 ohm resistor, 7 volt source, and then here is my resistance RL. As I mentioned a moment ago, I have 18 in parallel with, 18 in series with 11. So let's just make that a single 29 ohm resistance. And what I have now is effectively a practical voltage source in parallel with another practical voltage source. So if I convert both of those practical voltage sources into practical current sources, I'll be able to combine the current sources and combine the resistances. So let me make this work this way. Let's see what's going on in chat. How did I get to 47 again? Let me scroll up here. So 47/18 times 18. So I just multiply this current times this resistance using Ohm's law to get my transformed voltage source. And luckily for me, 47/18 times 18 is really easy. So let me just throw a set of terminals here. So we're going to have 47/29 in parallel with 29 between my red terminals. Between my green terminals. We are going to have, so 7/14, which is just half an amp. In parallel with 14. Here is our resistance RL. And so now I can see that I just have 2 current sources in parallel and 2 resistances in parallel. So 47/29 plus 0.5. Hold on, 47/29 plus 1/2 is going to look like 123/58 in parallel with 29 times 14/29 29 plus 14. (406/43). Here's RL. So the resistance that makes maximum power transfer occur, RL needs to be equal to 406/43. And our maximum power is going to be 1/4 times 123/58 amps squared times 406/43 ohms, using our maximum power equation for practical current sources. Go back to the top. What would you like for me to explain, Aiden? How I wound up getting the 47 as a numerator. Great. Okay. So when I did my source transformation here, I wound up with an 11/18 amp source that was in parallel with a 2 amp source. 2 amps is the same thing as 36/18, if my mental math is correct. So 36/18 plus 11/18 is 47/18. Then I multiplied 47/18 by 18, which gives me 47. All right, what's next?
On the fall 2019, problem 19, I have a question about that.
Sure. Do you want me to just...
Well, so I see that you're doing what I think is current division
I am indeed.
to find I3. I just don't understand why you have R2 on the top of
So
that.
I actually worked this problem out on Monday. Riley had the exact same question. So let me explain just that part really, really quickly. Okay. So, and then if you need further explanation, you can look at the video on Monday. So let's just say that I have 2 parallel paths and I'm trying to apply current division, right? So let me draw a circuit here. So I have some source current IS. I have a resistance R1 in parallel with a resistance R2. And I'm interested in finding the current flowing through the resistance R1, which I'm going to call I1. Okay? Because that's the situation effectively like we have in the problem that you're asking about. So how I taught things in class is that that current I1 should be the current IS multiplied by 1 over R1 divided by 1 over R1 plus 1 over R2, right? So what I'm going to do is I'm going to play around with that a little bit here. So I'll have IS, my 1 over R1 is still going to look just like 1 over R1. But now for this one, I'm going to have 1 over R1 and I'm going to choose to multiply by R2 over R2. And for this 1 over R2, I'm going to choose to multiply by R1 over R1. So all I'm doing is just multiplying each of those reciprocals in the denominator by a fancy version of the number 1. So what that gives me is IS times 1 over R1 divided by R1 plus R2 divided by R1 times R2. I have a 1 over R1 in the numerator and an R1 in the denominator of the denominator. And so those guys are going to cancel each other out. And so I'm going to have 1 over this thing. So that's just going to be the same as IS times R2 over R1 plus R2.
Okay, yes, sir. Thank you.
Yeah, so that's the relationship that I used when I solved this problem way back in 2019. That method of applying current division is what is taught in most textbooks, but I no longer like that particular method because I find it to be rather confusing, and most students do as well. So effectively, you wind up having the resistor, the path you're not interested in the numerator, and you're not using reciprocals. This only works for exactly 2 resistive paths in parallel. The method that I taught you guys using the reciprocals works for any number of resistive paths, which is why I teach that version now, because it's just so much more powerful and so much more applicable. So I just made that solution 5 years ago and never updated it. So sorry, it's confusing. Anything else I can help you all with? Alrighty, well, I don't know how many or if any of you guys intend on taking your exam tonight, but it is available on Canvas in a standard time format and an extended time format. So for those of you that have applied for extended time, there is an option for you. Just to remind you all, you don't have to take the exam tonight if you don't want to. You will also have an opportunity tomorrow afternoon, tomorrow evening, Friday afternoon, and Friday evening. Any of those time slots which work for you, just take that particular test. You're only allowed to take one version of the test. So you can't take one, do poorly on it, and then take another one and try to get a better grade. I consider that cheating, and I will happily fail you for doing that. So I'm just being very clear about it. Things are currently set up so that you can see your score as soon as you finish the test. So the score on your test overall, but you won't be able to see how you did on individual problems until I enable that after everyone has completed their test. As I mentioned earlier, please make sure that you scan your work after you take the test and upload it to the appropriate online submission portal. And just as a heads up, I intend on staying up this evening and working on the other versions of the test. So right now, the only one that you can see on Canvas is the one for Wednesday evening, but I should have at least the Thursday versions of the test up either late tonight or very early tomorrow morning. All right, you guys have a great rest of your day. Study if you feel like you need to study, and good luck on your exams. And just to be clear, we will not be having a lecture or anything like that on Friday. So that's just for people that want to take their test at that time.